Hello. So this is a little bit of a a tangent, a side topic, but it occurred to me that I had forgot I didn't post about this yet, so I'm going to do so now. So we had talked about two different ways of describing potential energy due to gravity. Um, that it could be mgh, but then we also looked at this way where we integrated uh, Newton's law of gravity and found that it was negative gmm over r. And the issue is that these two pictures better reconcile. They better be the same thing if we look at the appropriate conditions. So basically, mgh is only valid when the change in r is very small. And we can show that correspondence if we use a Taylor series. So it's kind of a cool application of like a Calc 3 idea. And so I wanted to have it on a video for you because I like drawing attention to these connections between your math and your math courses and what we talk about in physics. So it's a little bit of a side note, but let me show you how this works. So let's see. So recall a Taylor series. So the idea with this is that, and I think you see this in Calc 3. Excuse me. The idea with this is that if you have some function, you have some function or whatever, and you look at it at some point, you can approximate the function around that point using a series expansion. So what that looks like is the value at the point plus a derivative of the function evaluated at that point times quantity x minus that point where you're evaluating it plus 1 over 2 factorial plus a second order derivative term times an x minus x naught squared, etc. And where I'll use HOT to represent higher order terms. So you could have higher order terms which have large higher order derivatives and powers of x minus x naught. And in other words, you can write this concisely as a sum. It's kind of this complicated looking thing where you have a sum of derivatives times powers where you subtract off the point where you're interested in looking at it. And a special case of this is where x naught is 0, and that's called the Maclaurin series. But that's just kind of a detail. And we're going to make use of this this series expansion idea or we have sort of already, maybe we've talked about this. One circumstance where it crops up is when you're talking about small angles. So something that's kind of interesting. So as an example, consider sine theta when theta gets small. So we can apply this idea, all right? So around theta equals 0, in other words, sine theta is going to become sine of 0 plus the derivative of sine, which would be cosine of theta, evaluated at theta equals 0 times the quantity theta minus 0 plus higher order terms. So this is just the first two pieces. So what does this look like? Well, sine of 0 will give you 0 plus sorry, come on, plus cosine of theta when theta equals 0 would give you 1 times theta minus 0, so times theta. So in other words, sine of theta becomes theta when theta is small. So this is a small angle approximation. And you can see this same thing if you look at tangent. If you look at tangent, when theta gets small, it looks the same. Tangent goes to theta when theta is small. And these can be really useful. We'll talk about this with regards to the pendulum. So we'll come back to that idea when we talk about the pendulum. Now, back to gravity. On the one hand, so we have these two different pictures. On the one hand, we say that the potential energy due to gravity is mgh. And recall, this came from noticing that the potential energy is the negative work done by gravity. And if you imagine, you know, like an object where you lifted up some height, let's put it like this. The work that gravity is doing in that situation is negative, or it's negative the work that's done by gravity, so it's negative mgh, so it's mgh. Okay. And then at the same time, we looked at this picture where when we're talking about like a planet, and you know, we were in the context of like big distances, we have a force of gravity, and you imagine, you know, you go some to some higher orbit or something like that. The main thing being that the force of gravity is going to change. And in order to find the potential energy, you follow the same approach. So negative is the negative work. That's going to be the negative integral of the force of gravity dot dl. Now, in this case, we use our more complicated expression for the force of gravity, negative gmm over r squared. And the only thing that's going to matter is in the direction r. So this r dot dl is going to become, we're just going to become an integral over dr. In other words, the dot product is just picking out the change in height. And so we have an integral that's, if we pull out the constants, we have to integrate dr, or sorry, r, 1 over r squared. It's maybe easier to present that as r to the negative 2 dr. And when you integrate that, you get negative 1 over r, plus some constant. And generally we choose the constant c to be 0. So as r gets large, the potential energy goes to 0. And we had sort of a cartoon of this. Looks kind of like this. Excuse me. And you can't get smaller than the radius of the Earth, and r goes to 0, etc. So in any case, it's always negative. And so yeah, just to summarize, that the potential energy is negative gmm over r. Now, let's see, is it still recording? Interesting. So the question then becomes, what really matters to make these two pictures the same is to look at the change in potential energy. So what we're really interested in is the change in potential energy. So we can state that as the potential energy r plus some little h minus the potential energy at r. Okay? And we want to show that equals mgh. Okay? So, in other words, we can state this as negative gmm r plus h over r plus h minus negative gmm over r. Does that equal mgh? Well, we can expand the potential energy as a function of h around h equals 0. So what is that going to look like? So in other words, our function of h is negative gmm r plus h to the negative 1. So what does this look like? Well, we evaluate it at h equals 0. So that'll be the first term. The negative gmm r plus 0 plus the first derivative gmm negative 1 r plus h to the negative 2. So that would be the derivative evaluated at h equals 0 times the quantity h minus 0 plus higher order terms. So, and then when we, simplify this, what does it look like? It's negative gmm over r plus, this negative will cancel, gmm So we're evaluating this at h equals 0. So this becomes over r squared because we're adding only 0 to it. And then times a factor of h plus, other terms. So that's the potential energy as a function of height expanded with the Taylor series. Now, if we look at the change in potential energy, what do we have? Well, let's add these together. So we have negative gmm over r plus gmm h over r squared plus dot 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 minus the default, so minus the initial, which would be minus gmm over r. So notice we pick up, this term is duplicated, so that one will cancel. And then we're left with this, gmm h over r squared. Well, recall, what is gm big M over r squared? That's the same thing as little g. Remember, the force of gravity equals the mass times the acceleration of gravity at the surface of the Earth. So in other words, big G m over r squared, this is the same thing as little g. So we've recovered, so this is g mh. The change in potential energy is equal to mgh. So we've showed that this is the same thing via Taylor series expansion. So I think this is a cool thing just to kind of be familiar with. It's an example of how these sometimes pretty abstract mathematical ideas, such as the Taylor series expansion, like what's that? What are we going to use that for? Some of them have direct and powerful application in relevance in physics problems. So the farther you go, the more tools you'll have in your toolkit. So yeah, I think it's a real endorsement of some of those mathematical tools that you learn in calculus and how they connect really, really powerfully with ideas in physics. So, all right.